systems, here's some of the iron-based systems, and in each of these cases, what we see is our superconductivity is in proximity to an antiferromagnetic state that we've been able to suppress. Okay? So, in each case, we have what I would call a fragile magnetic state, adjacent to or in the middle of our superconducting dome. So let's rephrase our desire. Let's try to find more transition metal-based fragile magnets. Okay? That's a refined thing. It's starting to be a slightly sharper question. Okay? Now, we can say let's choose our usual suspects. Let's take iron, cobalt, nickel. We can include chromium. These are good for intermetallic compounds. Okay? If you say, hold on, I'm missing your favorite transition metals, here's one of your favorite transition metals. We could look at all of these, but look, these guys are enough. As a matter of fact, if I look just at cobalt, I hope I can illustrate that this is already a lot, unless you're trying to do something to narrow your phase space. Because now, instead of having Pearson's books, I can have Pearson's online or on my little laptop. I can look at all of this data, okay? And if I look at just cobalt materials, if I look at cobalt in a tetragonal unit cell, a ternary compound, so I'm taking a subset of a subset of a subset of cobalt, I end up with 1,158 hits. That's still a lot to ask my friend, the computational physicist, to look at all 1,158. I get taught new words in languages I don't speak, and I don't think they're polite words. So let's see if we can narrow this a little further. All right? If we're using computational efforts, can we somehow try to figure out a nice way of defining fragility? Because not all of those cobalt compounds are magnetic or fragile. Okay? So we want something that indicates fragility, and computationally, pressure on a pure compound is much easier to calculate than doping at ambient pressure, because doping introduces disorder. If you want to do it honestly, you have to do supercells and all sorts of stuff. On the other hand, pressure on a pure compound, that is something that's more manageable. Now, grossly, this means we're going to focus on bandwidth rather than band filling, but that's okay. In the iron arsenides, at least, we can look at the phase diagram. Here's temperature versus pressure. Here's temperature versus doping. In both cases, we suppress an antiferromagnetic orthorhombic transition, and we have our dome of superconductivity. If something is fragile, it tends to be fragile as you perturb it in either way. Okay? That's not a guarantee. That's not a mathematical proof, but it's not surprising either. Okay? So, what do we try to do? Experimentally, we're trying to identify promising candidate materials by data mining, by literature searches, by intuition. Okay? We can measure the magnetization, electrical transport, and now with a wonderful postdoc from Frankfurt, Elena Gatti, we can measure specific heat under pressure, okay, up to 1, 2, or 8 GPa. We can use chemical substitution. We don't have any problem with that. And we can try to look for systems that look to be fragile. Now, that takes a lot of time. So computationally, we're trying to work with computational groups to see if we can come up with ideas of benchmarking or understanding when things are fragile or not fragile, okay? Once the methodologies are considered reliable, we then want to use them to make first cut identifications, and then we want to see if we can either prove or refute them and feed back into this, okay? We've started trying to do this. This is something that Rosa Valente's group and my group have been doing for the past 4 years or so. It's not easy, okay? Fragile magnetism is still difficult, and one of the rate limiting steps right now is figuring out which of these cobalt compounds may even have moments. So we're having to now figure out how to generate a generalized susceptibility computationally to see which ones might be magnetic and then go forward. But this is part of the negotiation with computational groups. You, as the experimentalist, need to ask increasingly sharp questions, sharp enough that the computational groups can then try to implement them. Because just saying, hey Rosa, find me a new high TC, I learn new words. Okay, fine. So, third motivation, and this is where it becomes sort of fun. Okay? We're getting to the part that is interesting. Okay? We can look for known and unknown unknowns. By the way, this is a concept that was developed in NASA long, long ago. One of the administration of former Bush used it also. I think Rumsfeld paraphrased this, but I don't give him credit for this. This is an engineering term that NASA has used for a long time. And it's actually interesting because there are known unknowns and there are unknown unknowns. And let me give you an example of this. This is not completely gibberish. So, known unknowns: run across the series or study a family. Okay? So, let's say I grow a rare earth XY material. I grow neodymium silver diantimonide. Okay? If I grow neodymium silver diantimonide, the rare earths are wonderful because they're all more or less the same valence, they're all more or less the same size, and if I grew neodymium silver diantimonide, I'm pretty sure I can grow praseodymium and samarium. I probably could grow promethium if someone would give me some, but I have trouble getting promethium. Okay? Has something to do with the liver, if I remember correctly. But if you can grow one rare earth, you can grow more of them. And in many cases, you can grow all of them. So if I happen to grow neodymium silver diantimonide, I know there are probably other rare earths, but I don't know what their properties are. It's a known unknown. Okay? So in our group, we have done run across the series, meaning we basically find a rare series and just go across the whole thing just to see what nature offers us. We did this with the rare earth bismuth platinum, diantimonides, nickel germanides, borocarbides, silver diantimonides, silver germanides, quasicrystals, and rare earth transition metal 2 zinc 20s. We did it with several others as well. The reason we do this is because it lets us know what anisotropies we have, what ground states we have. In some cases, how superconductivity interacts with the magnetism. In some cases, we discover amazing things in the non-magnetic rare earths. In some cases, we discover amazing things in the hybridizing rare earths. In some cases, we discover things in the local moment ones. Often what we discover, we then put aside for a decade or two and then come back because this is now the library that we can design specific materials and ask sharp questions from. Okay. Fine. We can also explore within a given structure class. We already saw an example of this. We knew barium iron 2 arsenic 2 exists. We know strontium iron 2 arsenic 2 exists. What about calcium? What about magnesium? Again, these are known unknowns. Okay? Again, also what I call pejoratively, but it's my own group, I can call it that, clever monkey experiments. Okay? So, it sort of makes sense. Now, let's talk about the other one, because this is where it gets fun. This is where we're now starting to whisper to the unicorn, come, ideas fill my head. Okay? This is how you try to get ideas, looking for unknown unknowns. Okay? These are directed but somewhat unfocused searches because you don't quite know what you might get. Okay? And let me give you two examples. Okay? Something I call deep peritectic and something I call we find solutions. Okay? Deep peritectic. This is going back to yesterday's talk. Here is a binary phase diagram, platinum and tin. Okay, here is a congruently melting material, platinum 3 tin. I don't know anything about it. I'm sure it's been looked at. Don't really care for today's talk. Might be really fantastic. Grow some. Let's see. Okay? On the other hand, what I'm interested in here is this side. Look, these are incongruently melting materials. Platinum tin 4 is incongruently melting. As a matter of fact, if you try to grow this by just combining platinum and tin and cooling down, I will get platinum 2 tin 3, platinum tin 2, platinum tin 4, and some tin. It will be a mess. It will be horrible. And you know what? This is what I call a deeply peritectic compound. This is sort of scientific slang, but what it means for me is probably this material has not been studied in single crystal form unless someone from my group or one of my students or one of my former students has looked at it. This is something you only get a single crystal by doing solution growth. The other nice thing is they're generally at low temperatures, and you can often find materials that are really benign. Platinum, tin, nothing poisonous, nothing toxic, nothing worrisome. Let's grow it. I can have my undergraduates do it just sort of for fun. Okay? I have no idea what it's going to be like. Okay? So, here it is. We can grow it by coming in underneath this peritectic, 4% platinum, 96% tin. It loves to grow. Huge. Great. So what? Well, we can measure the resistivity, and the one thing I'll say is sometimes with materials you have to really sweat and grunt to get it to have large residual resistivity ratios. The residual resistivity ratio is how much the resistivity has changed from room temperature to base temperature. If it's a very disordered material, they're more or less the same. If it's highly ordered, it can be a large ratio. Here we have residual resistivity ratios modulo 1,000. Okay, so it's a high purity metal. That's cute. On the other hand, if I look at the magnetoresistance, remember it's dropping from room temperature to low temperature by a factor of 1,000. When I apply 14 Tesla, it's actually increasing. This has 500,000% magnetoresistance. Barbaric units, but those are the units of magnetoresistance. I think just between us we can say it's big. Okay, huge magnetoresistance, quantum oscillations in any property you happen to measure. We thought this was sort of neat at the time. Okay, now this was before all the obsessions or awareness of topological materials, Drac, etc. So we just sort of put aside, look, it's an incredibly pure, huge magnetoresistance. We don't understand it, but it's sort of neat. Now, on the other hand, with the onset of all the Drac and Weil, etc., I've noticed a correlation that often these materials have large magnetoresistance, possibly associated with the dispersions that you get from these features. So I convinced my colleague Adam Kaminsky, who does ARPES, to look at it. I said, look, intuitively, I think it should have some interesting features. When he looked at it, we discovered something called a Drac Node Arc. Okay, so indeed there were Drac-like features. How did we come upon this material? By exploring. Okay. Now, other example. Let's look for another example in the Deep Peritectic Project. When we grew the rare earth transition metal 2 zinc 20 materials, we figured out how to work with zinc. Zinc is non-toxic. By the way, no one asked me to play Eat, Wear, Kill. I'm really disappointed. Zinc is non-toxic, okay? But it has a high vapor pressure, so you have to figure out how to play with it, okay? We mastered that. Having mastered it one summer, I had 2 women undergraduates and I wanted them to try to grow some materials, but I didn't want to kill them. So this was actually a nice way. Scandium and zinc are non-toxic. We can play around. There's very little known about scandium, zinc 12. It's supposed to be a tetragonal material. Let's look at it. Maybe I'll see some weird magnetism in scandium. It's possible. The first growth, we got that. That is not a tetragonal crystal, okay? My calibrated eyeballs tell me 1, 2, 3, 4, 5. If the number is 5, I actually have colleagues. Alan Goldman is my scattering colleague. He's obsessed with quasicrystals. I just said, okay, hey, to the students, hey, watch this. I called Alan, I said, hey, Alan, the number is 5. Alan says, I'll be right down. Okay, so he comes down. And we had discovered the second example of a stable binary quasicrystal in the scandium zinc family. As a matter of fact, Peter Samueli was saying, well, binary phase diagrams, they're all known. No, we had to redefine the damn scandium zinc binary phase diagram. We found an exposed liquidus for this quasicrystalline phase. That's not my job. I shouldn't be having to do this. On the other hand, it was sort of neat. New quasicrystal. Now, scandium zinc non-magnetic. On the other hand, the scandium zinc 12 is what's known as a crystalline approximant. It is a non-quasicrystalline material, but it has motifs in it that look sort of like it wanted to be quasicrystalline. And one of the things we speculated was, oh, maybe you have quasicrystals nearby crystalline approximates and they're just deep peritectics. So let's see if we can find another example of this. So a few years later, Alan said, look at cadmium. Because gadolinium cadmium 6 is a crystalline approximant, okay? I said, oh, this is gorgeous. What we did is, we came in for our first growth. I said, okay, we're going to grow the rare earth cad 6, okay? But we're going to cool way down. And what we did is we discovered a new phase, a rare earth cadmium 6 quasicrystal, okay? So we again redefined the phase diagram. And this quasicrystal is nice because we can get it for gadolinium, but we can also get it for yttrium, which is non-magnetic. We can go all the way down to thulium. We could play quasicrystalline games again, but in a binary system. Okay? All right. Let me give you another example of known and unknown unknowns. We find solutions. Okay? So, basically, if we think of the pnictide column, we've had a lot of fun playing with bismuth and antimony. When we got the arsenides, we could look at arsenic and indeed phosphorus. Essentially, what we're doing is narrowing the band. So, big fat band, narrower, narrower, narrower. Well, come on, I want to go to the limit. Nitrogen. Nitrogen is tricky. It's not easy to do solution growth in nitrogen because there aren't many solutions that have nitrogen in it. Okay? So, I was looking through phase diagrams when I'm sad and lonely, or it's a nice afternoon and I just want to sort of enjoy fantasizing. I look at phase diagrams. That's my life. Okay? But I was looking at phase diagrams. Here's lithium nitrogen, and this is implying this liquid, if it's real, has lithium and nitrogen. Okay, now, it might not be. This might be just a schematic, but I wanted to check. So, we could buy some lithium-3 nitrogen, polycrystalline. We can put it in lithium using these tantalum crucibles, heat it up, cool it down, and we end up with big, honking single crystals of lithium-3 nitrogen. Okay, neat. Okay, now, what can we do with it? Well, we can try to substitute things in. This is a semiconductor. We tried to substitute things in. We tried iron, and we ended up finding out that dilute iron in lithium-3 nitrogen is a more anisotropic local moment than any rare earth I've ever seen. And this is because it's in a linear configuration, and linear configurations are exceptions to the Jahn-Teller theorem. So this is a proof of principle that you can have high anisotropic magnetism in transition metals, and that gets rid of all of the problems with rare earth scarcity. Okay? Now, in a similar manner, if we're interested in looking for rare earths or rare earth-free magnets, we can try to look at unexplored parts of phase space. Volatile elements have been difficult because often the quick way of making things is arc melting. It's hard to arc melt something that goes gaseous. So we found, if we look at, for example, phosphides, the iron phosphorus eutectic on the iron side, the manganese on the manganese side, the palladium on the palladium side, these eutectics, even though they have a fair amount of phosphorus, if you get the phosphorus and the transition metal mixed, these are eutectics that you can actually work with and then add other materials to explore for new ternary or quaternary materials. And we've actually discovered several new hard ferromagnets that way. So, I hope I've shown you how looking for unknowns can feed into wanting specific compounds or wanting specific ground states. In reality, all of these feed into each other, okay? And since I have 2 minutes left before I start the questions, I want to leave time for questions. Okay? Let me give a final example. This is a current ongoing example. We touched upon this yesterday when I was asked about quaternary phase diagrams. We wanted to look at calcium, potassium, iron 4, arsenic 4. Okay? The reason was, okay, it had been found in polycrystalline form that this could have superconductivity as a line compound at 35. Okay? These two fine gentlemen figured out you could take the quaternary, go to a pseudo-ternary. You could grow crystals. We went over that yesterday. With crystals, we could study the anisotropic properties. Okay? So we could look at the resistivity. It has a mildly anisotropic resistivity, good triple R's, sharp superconductivity at 35 Kelvin. Hc2 is very similar to what we saw for the barium potassium because chemically it's quite similar in terms of doping. Okay? And with crystals in hand, just to give you an idea again, once you have the samples, you can start doing many, many measurements. Anisotropic properties, ARPES measurements, we could look at tunnel diode measurements, we could look at the effects of pressure, we can look at the effects of NMR, we can go down, it opens the physics to us, okay? So we started with really wanting the material, we studied the basic properties, okay? We were surprised when we saw a half collapsed TET phase, and now we can start looking at variance. Okay? We wanted to see if we could induce magnetism. So, having decided that a quaternary compound was not enough, we could try to grow a quintenary compound. We can try to dope in cobalt or nickel, okay, and discover a phase diagram quite similar to what we discovered for the 122s, but with a new type of magnetism. Okay? So, basically, what I want to emphasize is a healthy new materials program has these various motivations. They tend to feed into each other. Advances in one help support new discoveries or new research in the other. Okay? So, this is work that's been supported for decades by Department of Energy, Basic Energy Sciences. More recently, over the past 4 years, the Gordon and Betty Moore Foundation have been generous and supported this as well. Okay? And I started with a conclusion, so I don't need to go over those again, but we need to be both humble and ambitious as we go forward. Humble in recognizing there are many unknowns that can only be discovered by broad exploration. I don't think we are ready for materials by design. I don't think the computer is going to tell me what next discovery I'll make. You need to go into the lab, get your hands dirty, burn your fingers a little, and find stuff. Okay? Now, ambitious, we need to strive to make these discoveries more frequent, and I think we need to take advantage and work intimately with our computational colleagues and try to advance how we can answer and ask sharp questions. So I think this is going to be a vital and productive field for decades to come, and I thank you for your patience, and I will happily take any questions.